Now I'm going to talk about ventilation and dead space. I'm going to leave this up here, but there's just a couple of points I wanted to make. Whenever you see a dot over a letter, like V dot, it represents a rate, volume per unit time. Q dot would be the same thing. This is ventilation. Expired air, V dot E, equals frequency times our tidal volume, V dot T. Tidal volume is the volume of air moved in or out of the lung for each breath. Tidal volume is broken up into two different components, dead space volume and alveolar volume. Alveolar volume is the air that ends up in the alveolus. The dead space volume is the air that ends up everywhere else. That would be the bronchi, the trachea, bronchioles, even the nasal passages. Those are dead space. Those are regions in your respiratory system that are not participating in gas exchange. Tidal volume times frequency we call ventilation, equals dead space volume times frequency plus alveolar volume times frequency, which means dead space ventilation plus alveolar ventilation. Now, anatomical dead space I just mentioned, trachea, nasal passages, bronchi, etc. Physiological dead space includes alveoli that are either not perfused or poorly perfused. If an alveoli is not perfused, there could be an embolism there. Any air that gets into that alveolus is not participating in gas exchange. It's wasted ventilation. It's dead space. So physiological dead space includes alveoli that are not perfused or very poorly perfused. And again, I'm not going to go over all of these points. There are a couple of points, however, I think that are important to know. One is, whenever you're dealing with alveolar air, we have to look at the barometric pressure minus the water vapor pressure. And the water vapor pressure is always 47 millimeters of mercury at normal body temperature. Regardless of altitude, 47 millimeters of mercury. In fact, if you were at an altitude in which the barometric pressure was 47 millimeters of mercury, your alveoli would be filled with water. Another point I wanted to make is that we measure alveolar ventilation and CO2 production using different units. Body temperature pressure saturated air or standard temperature pressure of dry air. That means we have to use a conversion factor of 863, and again, that's independent of altitude. You may actually find some books showing 0.863, and they do that because they usually measure V dot CO2 production, in milliliters per minute, whereas they measure ventilation in liters per minute. There's a 1,000-fold difference, so they make the correction 1,000-fold smaller, therefore 0.863. I would always advise people to convert all units to the same before doing any calculations anyway. Another pet peeve of mine is the word hyperventilation. Earlier I said that alveolar ventilation is frequency times volume. Well, for this purpose we are redefining alveolar ventilation, and we look at the alveolar ventilation equation here and rearrange it. We see ventilation has nothing to do with frequency and volume. It's only CO2. CO2 production divided by partial pressure of alveolar CO2 times 863. Hyperventilation then produces low CO2 when ventilation exceeds the need to maintain CO2 at 40 millimeters of mercury. We are hyperventilating. If ventilation falls to the point where CO2 rises, we are hypoventilating. So we determine ventilation in this sense based on CO2. The need to ventilate must be matched with metabolic rate. So when you increase your breathing, such as during exercise, we don't know if you're hyperventilating. Hyperpnea is the term used for increased breathing. Hyperventilation is the term used for reduced partial pressure of CO2. Here's another set of bullets that I will just leave up there. Then there's one point I wanted to make here, once you've read through these, and that's this alveolar gas equation. Alveolar PO2 equals PiO2 minus PaCO2, and that can be either big A or little a, because alveolar and arterial CO2 under most conditions come into equilibrium. So PaCO2 divided by R. And up here we can see what R is. This equation often causes confusion in students. It's actually a simple principle. PaO2, what's in the alveolus, equals what went into the alveolus, PiO2, minus what came out of the alveolus. Well, we can't measure what came out of the alveolus, but we can measure what went into the alveolus in CO2. PCO2 divided by R represents the amount of oxygen removed. Let's assume then that PCO2 is 40 and R is 0.8. PiO2 is 150 millimeters of mercury. 40 divided by 0.8 is 50. 150 coming in, 50 coming out, leaves us with a partial pressure of alveolar O2 of 100. It's a very simple principle. If I give you 3 apples and you eat 1, you have 2 left over. If I put in 150 and you take out 50, you've got 100 left over. We estimate what you take out by measuring the CO2 that went in divided by the respiratory exchange ratio. It's that simple. Dead space. We can calculate the dead space by first looking at the dead space tidal volume ratio, that is, the fraction of the total volume that is devoted to dead space. FaCO2 is the total CO2 because all CO2 exhaled must come from the alveoli. So that's the total CO2. FeCO2 is expired mixed CO2, which contains dead space air. That difference divided by the total gives us the fraction of the total volume that is dead space. We can also exchange fractional concentration for pressures as long as we keep everything in the same units. This is the VD-VT ratio. Since we can measure tidal volume, we can plug that into this equation and then solve for dead space volume. Once you know the dead space volume, you can then easily calculate dead space ventilation. Simply dead space volume times frequency is dead space ventilation. One possible reason for increased physiological dead space is emphysema, for example. Emphysema not only causes airway resistance and airway collapse, but because the alveolar walls are being destroyed, we end up with effectively larger alveoli, in this case here, over here. And as a sphere increases in size, the surface area to volume ratio decreases. So the volume is increasing faster than the surface area when we increase any sphere size, even if it's irregularly shaped. I have a small alveolus, and this is the oxygen transport from the alveoli to the capillary, and a very large alveolus. Here we can see the oxygen diffusing into the capillary. But this alveolus is so large that the oxygen in the center of the alveolus does not have enough time to diffuse over to the wall and across the wall into the capillaries. Why is the surface area to volume ratio increasing? Always gives students a little bit of problem. Area is defined by the radius squared. Volume is defined by the radius cubed. So as a sphere increases in size, its volume is increasing much more rapidly than its area. So the surface area to volume ratio is decreasing. And this gives us some dead space. Some of the air in this alveolus is not going to have time to diffuse to the alveolar walls and across into the capillaries before we exhale again. Therefore, dead space. Now I'm going to move to my ventilation model, and we'll talk a little bit more about alveolar ventilation. In this computer simulation, I'm looking at 2 graphs here. Ventilation, alveolar ventilation on the bottom, and alveolar PCO2, alveolar PO2 on the y or vertical axis. And this represents the curve for any particular set of conditions. These boxes represent the calculated value for alveolar PCO2, alveolar PO2, inspired O2, and alveolar ventilation. And the variables in this red box here are things that we can change. I can change barometric pressure, fractional concentration of inspired oxygen, metabolic rate, R, and ventilation, either frequency or volume. And this we'll just ignore. This is for a more advanced topic. One of the things that I often ask my students is, what do you think will happen if we go to 1/2 atmosphere, barometric pressure 380 millimeters of mercury? That represents about 5,500 meters in altitude, approximately the base camp at Mount Everest. What will happen to alveolar PO2? They always tell you, correctly so, that alveolar PO2 will go down. When I then ask them what happens to alveolar PCO2, they always answer PCO2 goes up. So let's try that. 380 millimeters of mercury, and alveolar PO2 did go down. It's down to 21 torr, but nothing changed with PCO2. So why did nothing change with alveolar PCO2? Well, PCO2 at sea level is virtually 0. PCO2 at high altitude is also virtually 0, actually a little bit less than at sea level, but still virtually no CO2 in the atmosphere. So why didn't the PCO2 go up as most students would have guessed? One thing to remember is that all of the CO2 in the alveoli comes from metabolically produced CO2. If I have not changed anything but altitude, haven't changed metabolic rate, we would not expect the CO2 to change, and in fact it did not change. I now ask, what would happen to an individual who is experiencing this level of hypoxia? What would be the physiological response to this level of hypoxia? Students correctly guess that ventilation will go up. So let's bring ventilation up. And we'll stop here at 29 breaths per minute. I could change tidal volume, I could change them both, but we'll just stick with frequency for the moment. The PO2 did go up. It's now up to nearly 50 millimeters of mercury. And the PCO2 went down. PCO2 did not go up, it went down. This is the definition of hyperventilation. This individual is hyperventilating in order to drive oxygen up. But hyperventilation by definition means low CO2. And we have PCO2 at nearly 17 millimeters of mercury. Let's just change the metabolic rate for a moment. Let's double this to 470. Now, what's going to happen to alveolar PO2 if I change metabolic rate and alveolar PCO2? Think about it for a second. Okay, let's do it. Well, the PO2 fell, metabolic rate went up, PCO2 went up. So PO2 came down, PCO2 went up. This is what the students normally predict would happen at altitude, because there's this idea that somehow there's a reciprocal relationship between oxygen and CO2. And that derives from the fact that we normally think of exchange as the way we do when we go to a store and we bring back a shirt that somebody gave us for our birthday or Christmas, and we say, I want to exchange this for another shirt. So you give them something, they give you something back. Well, gas exchange is not really that type of exchange. Oxygen moves in and out of the alveoli and blood, back and forth, totally independently of what's happening to CO2, and vice versa. CO2 moves independently. So it's not really exchange as we normally think of it. One of the things I often tell my students is, what you hear is not always what I say, because what you hear is based on what I'm telling you plus what your experience is. So if your experience is that exchange means 1 for 1, then when I tell you gas exchange, that's what you're thinking. PO2 went down because we didn't change ventilation. So now, how are we going to bring the PO2 back up and the PCO2 down? We want to match ventilation with metabolism. PaCO2 is back to 40, PaO2 is back to 100. Alveolar ventilation is now 8 liters per minute. At this point, even though breathing has gone up, frequency has doubled, we nonetheless are not hyperventilating. Remember, hyperventilation means PCO2 has fallen. PCO2 is normal. Ventilation has gone up. We call this hyperpnea. In fact, because I've only changed frequency, we would call it tachypnea. Tachy meaning rapid. Well, that ends this discussion on alveolar ventilation and dead space.